your circuit, your electronics should be capable of doing your experiments. So basically you need to do number of experiments, NMR experiments, in such a that you will get a final result. So this is actually triple resonance probe circuit, triple resonance probe circuit. And you will see that X and Y means you can set one more nuclei. One is a hydrogen that is fixed. Another one you can set it to carbon. Another one you can set it to nitrogen. So if in case of a biomolecular material, protein or something like that, then you can set that. You can detect them actually by using triple resonance. So you need to have a 3-channel spectrometer. So this is my first probe design during my PhD time. And as I told you, so proton is the reference frequency for any other nuclei. So what magnetic field you are setting, that is what your proton resonance frequency. Based on that, all other nuclei resonance frequencies are changing. Means these are all Lambda frequency only. So you can calculate them. So you will get a pre-induced decay, and then you will get Fourier transform them, and you will get a spectrum. So I already told you what you mean by homogeneous and inhomogeneous. You can see in the NMR tube, electromagnetic radiations are in a different orientation. That means that they are not parallel. So this means the first cube will see a parallel line in a different way. The second cube will see a parallel line in a different way. So that means that it will give you a inhomogeneous spectrum, something like the bottom one. If you do shimming, there is a process called shimming in the spectrometer. If you do shimming and make your electromagnetic radiations are in a parallel lines like this, then your chemical shift C by the same molecule will be same. So you will have only one resonance. So this is actually artifact, and this is actually real signal. So shimming is a process which is being using that room temperature shim stack that I told you when the magnets are being explained. Okay, so you will have a additional magnetic field that will be making this high magnetic field as a homogeneous one, and then this is the height adjustment. So you adjust the height based on the coil height, so that you will get a good sensitive signal. So as I told you, your radio frequency pulse has been applied either x-axis or y-axis. Then your spin precision along z-axis will come to transverse plane, and this spins can be go back to Zeeman axis as time progress. So that is what you are measuring as a pre-induced decay, something like this. And you can say that MXY is the transverse plane magnetization, and it will be initially, once after the pulse is applied, it will be very high. After that, the oscillation will start, and you will have a very decayed signal. So you can get a chemical shift, delta equal to omega minus omega ref, omega divided by omega ref. Omega ref is the known signal, internal calibration, something like that you can say. So you are with the known signal, you can get a chemical shift delta. So hereafter we will use a chemical shift as a name. When you see a single sharp line, that is called chemical shift. You will see multiple line, that is called chemical shift. If it is splitted pattern, like a multiple pattern, it is a chemical shift only, but it is a there is an interaction between the neighboring atoms happening. That is what you are seeing, a multiple peaks. So those things you will see, but you will be learning from me what is chemical shift. So hereafter I'm going to use this term called chemical shift or delta. Okay, so here in this case, why this oscillation is happening? This is because your T1 and T2 has been influencing your nuclei to reduce, to decay its high energy. So initially it will have a high energy, so it can relax its energy by two methods. One is lattice site interaction. Another one is spin-spin interaction. That means one can assume the total matrix as a lattice and it exchange its energy. Another one, the same spin can see the similar spin like that, and then it exchanges its energy. Then it is called a T2. So it's a two type of interactions. So once you get this FID, then you simply need to Fourier transform FT, and you will get a spectrum. So the spectrum basically, like this. In solution state NMR, normally you will have a spectrum from 0 to 15 ppm or 20 ppm. So this scale is called chemical shift. The scale is ppm, part per million. You can say, label it as a chemical shift. So always TMS is a reference. What is TMS? TMS is nothing but tetramethylsilane. The structure is shown here. Silicon is placed center, and then CH3, 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 CH3 is bonded. So this is called tetramethylsilane. This particular structure will always give you zero resonance. So this has been taken as a reference frequency, and then all other signal will be, with respect to this, will be taken as account, and then you can analyze them. So normally people will say that upfield and downfield. What is meant by upfield? Upfield means it is close to zero. That means that there are no other molecule other than the tetramethylsilane, like closely shielded molecule. So if anything happens, anything de-shielding is happening, then your signal will go away from zero. So that means that CH3 thrice C is away from zero, and CH3O is away from zero. So this is because of oxygen. One is because of terminated carbon. One is because of oxygen. Oxygen has a lone pair, and it can withdraw some electron. So the electron interaction between the proton will influence that de-shielding. That means a downfield movement. So basically, as I told you, one is upfield movement and downfield movement. So if you have a halogens, chlorine, bromine, iodine, nitrogen, oxygen, something like that, then the electrons they are known to prone to withdrawing electrons or de-shielding or electrons. Proton is a very small molecule, and they are very influenced with this type of interactions. So this is called correlation. Actually, the correlation can be taken into account. One is because of this neighboring molecule, there will be some de-shielding is happening. That's why you are getting a chemical shift in a different position. So you see, you are getting a proton signal, one CH3 in very close to 0 ppm, and OH in a different position. So based on the understanding, based on the different experimental trials, people understand that two different mechanism is happening. One is a shielding, and another one is de-shielding. When it is purely CH3, then it is a shielded position. When it is a CH2, CHOH, then it is a de-shielded position. So basically what happens now, how much your nucleus is seeing the magnetic field, that is what you want to see from this spectrum. This is actually some sort of influence of different nuclei to a CH3 fragment. And you can see them that if it is a sp3 bonding, then you will see that very close to 1 ppm you will have a signal, proton signal. If there is no such things happening, sp2, then neighboring has something, nitrogen, oxygen, and some other nuclei, then your de-shielding can happen. You will have a ppm values of more than 2.5 to 4.5. You see, benzene has a range from 6.5 to 8. So some and OH also, OH will play like anywhere within this spectrum. It can go anywhere, but most of the time it should come, by theoretically it should come 9 to 12 ppm. So what you are getting from the NMR, proton NMR spectrum, one is a number of signal and position of the signal and intensity of the signal, and then spin splitting of the signal. So until now, what we have seen is only single line spectrum. So I have explained you what is single line spectrum, but it is possible that your neighboring spin is interacting with them, then your spins are split with the spectrum, so that the same environment will give you in a different shape. And then intensity of the signal will give you the accountability of your proton, number of 1h. And then the position of a signal will tell you that where this unique environment is positioned. And you see the bottom slide, you can see them. CH3OCH will have only one line. Why it is giving you only one line? Because your oxygen is seen by the right side CH3 and to the left side CH3 is same. Assume that CH3 is a one type of molecule and that has a HA proton. That HA proton, even though they are in a different place, they see the oxygen in one way. So the effect of the oxygen to the proton is uniform, and the magnetic field see the CH3 is again uniform. So you will get only one resonance. But in the case of next example, ethyl chloride, you see CH3, CH2, Cl, you will see that two type of proton will be there. Two type of signal, resonance signal will get. Why you are getting two type of resonance signal? Because your CH3 is the farthest to chlorine, and your CH2 is very close to chlorine. So this CH2 will give you HB. HB means a proton signal, different signal, separate signal. HA means separate another signal, another position. So CH3 always close to 0 ppm in that sense. CH2 will be away from 0 ppm. That means the de-shielded proton HB and shielded proton is HA. The same analogy you can apply for ethyl methyl ether. So you will have a 3 different proton. So I'm just moving faster so that I want to cover solid state NMR as well. So I'm just moving forward. If you have any doubt, please ask me now. The point is whether you are having a unique proton, non-equivalent proton, or equivalent proton. That's it. That is the case. If it is if you understand how to analyze, understand the proton experiment, then it is applicable to all other nuclei as well. So the top one is the fingerprints for proton, and bottom one is the fingerprints for a carbon. So basically, x-axis is a chemical shift. So you will have a signal according to the fragments placed in your molecule. So how I can completely understand the structure of the molecule, how I can get a complete information. See, there are set of experiments that you need to run. One is 1H NMR, then you will get a proton position. Then you need to run carbon experiment and then depth 135. These two experiments will give you what are the fragments, CH2, CH3, CH, what are the fragments. You can clearly distinguish them and where it is exactly located. It is also given from these two experiments. And then you need to run a DQF-OC and HSQC. These two will tell you that what are the proximity protons, what are the proximity carbon to proton within the molecule. All this information will be combined, and then you analyze. You can draw a structure of a molecule. Of course, if you are a physicist, then what is molecule? You need to understand that. So molecule is basically an organic system, and if you want to understand the correlation between the molecule, between the two different nuclei, 3 different nuclei, or 4 different nuclei, then you need to go for this high dimensional NMR like HMBC, TOXC, HSQC, TOXC, and then ROC and NOC. These experiments will get you understand that what type of correlation is there, what type of dynamics is happening within the molecule. And then finally you can analyze and complete the protein structure by identifying the position of the resonance frequency from 2D, 1D, 2D, and then 3D. So this is a 2D experiment. You see this nitrogen proton. This is a 2D of a nitrogen proton, and this is the 3D experiment. You see that proton, carbon, nitrogen, 3 are there. So this is a 3D experiment. You need to have a 3-channel probe and 3-channel instrument in order to get this data done. So we'll until now we have understand that. Yes, somebody is asking. Somebody is asking. Please go ahead and throw a question. No questions? Okay. So let me go into that further detail. This is actually fantastic, fascinating your life. Actually, I would say solid state NMR. So solid state, by using solid state NMR, you can do n number of experiments. You can understand many nuclear properties. So the basic starts from spin interaction. So I was telling you about that 1D 2D experiments. What is the 1D 2D experiment? 1D 2D experiments are manipulation of this chemical shifts only. Again, here, there in solution NMR, you will have a isotropic chemical shift, but in a solid state NMR, you will not get a isotropic chemical shift. You will end up with a chemical shift anisotropy. What is that chemical shift anisotropy? You have a symmetries of the system. I assume that you know what is meant by materials. I assume that you know what is meant by crystal symmetry. Okay, so if you know that, then this is the thing. Your position of the atom is fixed in a solid state, and then your atom relating to the position is what you will get a symmetry structure. So what you get is a broad line like this in a solid state NMR. But this broad lines meant to be several things actually. In order to get information, you need to do so many experiments. So here is the point. Let me explain what are the interactions are there. Let me introduce to you so that you will try to understand in future or later. If you are interested, you just go deep into this area. One is spin interaction. What are the spin interaction? Two type of spin interaction. One is chemical shift. One is spin-spin coupling. Two spin can couple together. Okay. Another one is chemical shift. Whatever you are seeing until now, until I was explaining about proton experiment, that is the chemical shift. Another one is spin-spin coupling. That means one proton, another proton, they couple each other. Because of this coupling, they can result you some different results. The end results will be different because of the two spin couple each other. Similar, like in a one classroom, two people always talking each other. They found that their resonance frequency is matching each other, so they start exchanging their words each other. That is called spin-spin coupling. Okay, so isotropic chemical shift. Another one is isotropic chemical shift and anisotropic chemical shift. What is isotropic chemical shift and anisotropic chemical shift? This is the isotropic chemical shift. That means that individual resonance can be clearly isolated with respect to single resonance frequency, means that is isotropic chemical shift. If it is broadened by like this, then it is a chemical shift anisotropy, CESA, chemical shift anisotropy. So from spin-spin coupling, what you get? You will get a scalar J coupling, and then J coupling. You will get this information, and dipolar information also you get. All these informations by running different experiments. Whatever experiments I was listing you just before this slide, those experiments you need to run them, and then you need to get this information, scalar and then J coupling, dipolar coupling. This is get from ROSI and NOE, and then heteronuclear correlation is HSQC, HMDC, HMQC, and then homonuclear coupling is a COSI, TOXI, and NOE. So by running all these things, then you will end up a clear chemical structure. So this is completely for solution NMR, whatever I told. But sir, is it not applicable to solid state? Yes, it is applicable to solid state, but in a different manner, different sense. I'm going to show you those results and those pulse program and those experiments, but it will take some time to understand those concepts. But I will definitely get you into that. So after a chemical shift anisotropy in single crystal or powder material, you will always get a quadrupolar interaction. If your nuclei is a quadrupolar, means I was explaining very beginningly what is spin quantum number 1/2, what is more than 1/2. So that if you have end up with a quadrupolar nuclei, then you will definitely have a chemical shift anisotropy and quadrupolar interaction. That quadrupolar interaction is been splitted into two. One is isotropic quadrupolar shift, another one is second order quadrupolar interaction. So here is the point. So all these 5 interactions is the basic interaction in a NMR. One more interaction I have not told you. What is it mean? What is mean? That means spin rotation coupling. Spin rotation coupling. I will explain you in a few minutes what is spin rotation coupling. Because your sample itself being rotating in a one particular orientation. I'll show you in a minute how it will be. This is a solid state NMR. Normally people use a magic angle. Magic angle means theta is a 54.7 degree angle. Your sample will be rotating. You see that that top one is a cap and the bottom one is a something cup like that. Tumbler or something like that, and then top you will have a cover. So you put a powder and pack it and then tighten and then close it and then put it into the probe and then rotate it like this. So you see, this is a rotating. This rotational mechanism also influencing your spectral data. That's why I put this spin rotating coupling. So we will see that how it can be manipulated, how it can be used as an advantageous one. You see that in a static case, your sample will be along z-axis, and then you will get a spectra that is nothing but your broad spectra. When the magic angle reaching you 54.74 degree, then all your chemical shift anisotropy will be removed. If it is a spin-off nuclei, then you will get a sharp line. Sharp line is nothing but an isotropic chemical shift. So your P2 cos theta will become 0 here. And then when it moves away, then all your interactions like a dipolar interaction, chemical shift anisotropy will reintroduce them in the same experiment. So you need to be careful in setting this 54.7 angle. That's a real problem in solid state NMR. Again, this is actually this picture will give you a complete understanding from when these experiments, these magic angle experiments are started. You see this in 1997. They uses a 30 kilohertz spectral spinning speed. So even if you go to national laboratory, you will get like a 30 kilohertz nowadays. So we are still fighting to go for a high spinning speed, and it's you see now the available spinning speed maximum is 200 kilohertz. That means that this rotor is spinning up to this level, this spinning rotation, and then you get a NMR. You pulse the sample, and then you get a NMR data. Again, the challenges involved in this particular achieving a very high spinning speed is a big deal. And one has to invest their mind and money to get it done, and then do these experiments. So there are some different variety of caps are there, and while running this 200 kilohertz, your rotor itself getting hot. That because of the hotness, your rotor cap cannot go bad. It should not come out of the instrument. So you need to be aware of all the circumstances. What you get, so basically what you are observing from solid state NMR is an isotropic chemical shift. But in order to achieve the isotropic chemical shift, you need to spin the sample to a magic angle. You see that this is a comparison of solid state to liquid state. The top one is a solution NMR. The top one is a solution NMR. You will get only isotropic chemical shift. If you put in a static mode, you will get this fake pattern. This is simple powder. It is not spinning at magic angle. You will get a fake pattern. When you sample spinning in a magic angle, your lines will be resolved like this. And this has some meaning. This has some meaning, and your fake pattern also has some meaning about your orientation of your molecule. And this information can be extracted by fitting this experimental data, and you get the eta value. By getting this eta value, you come to know that what type of symmetry is this, what type of material is present inside. So basically, if it is a sharp line, you will say that a cubic symmetry. If it is like a peg pattern, you will have a threefold symmetry, or asymmetry, you can say. Again, this is an example of how the actual asymmetric thing is there. And this is static spectra. When you do magic angle, you will definitely get a sharp line like this, a new ISO. So that should be oriented along this particular point. So here I wanted to explain you how the shielding is been this because see all this influence all this mechanism, why this you are getting this peg pattern. You are getting a peg pattern because of your magnetic field is being seen by the nuclei in a different way, because if this is a powder material, this is not a solution. In solution you will have a Brownian motion. By tumbling and the Brownian motion, all interactions are averaged out, you will get a sharp line. But in case of solid state, it is not happening like that. So this is because of the shielding of the neighboring nuclei and to the local nucleus as well. So the local nuclear field is B local, has been defined by B0. B0 is the original magnetic field minus Bi. Bi is the induced magnetic field by the neighboring nuclei. You see this I nuclei, neighboring nuclei will be there. So because of that, you will have that this type of a spherical shape, spherical in shielding informations are there. So if you know that tensor mechanism, then this is very easy to understand them. See, you have a on axis and then off axis. So on axis is zxx, zyy, sigma xx, sigma yy, sigma zz. All other off axis has some information, but by removing them and you just do the symmetrization, then you will get your specific information, eta information, by solving this matrix. So tensorial, all interactions are tensorial form only. So you will have a isotropic chemical shift that is governed by sigma xx, sigma yy, sigma zz. So you can get it by fitting them the spectra, and delta is sigma zz minus sigma iso. So your shielding anisotropy can be extracted from this equation. And then asymmetry, you get a sigma xx minus sigma yy divided by sigma zz. So asymmetry informations also you can extract them. Basically your sample will be spinning along one particular axis, 54.7 degree angle. Again, all these are same thing. I'm just moving on. So what is happening inside the material? You will be you will see two information. One is spin interaction, another one is spin matrix interaction. That is a dipolar through space interaction. So dipolar interaction basically called through space interaction. So that is defined by Rij dd equal to mu 0 gyromagnetic ratio times of I, gyromagnetic ratio J, h cross by 4 pi ket vector of Rij cube. So this will give you the amount of interaction, how much it can be interact with the neighboring atoms. So you can definitely get a dipolar constant from this relation actually. So basically, your Hamiltonian of the dipolar interaction can be defined by h cross gyromagnetic ratio I, gyromagnetic ratio J, R power minus 3 square root of 3 into I into R, J into R minus I into J. So this will give you the Hamiltonian of the specific atom, which nuclei you are interested to see them. So again, as I told you, how these interactions are being nullified. So I was telling you this is at this particular point all this chemical shift anisotropy is 0, and the other point they will be reintroduced them. This is because of this equation. So if you solve them, then you will understand that what is the dipolar, what this Hamiltonian gives you the result is. So basically, in solution state, it is very easy, straightforward. You can get all informations like isotropic chemical shift, dipolar coupling, and quadrupolar coupling, J coupling. Everything you can easily achieved in a solution. But in the case of solid state, it is not that easy. You need to run several different experiments, and they have a specific way of implementations. Okay, so basically, the motion, the spin I'm talking about, the motional averages spin interaction basically. when all interactions are averaged out, then you will get a isotropic chemical shift like in a liquid state. But getting rid of them is a very, very challenging one. In liquid state, you will only see that a magnetic and magnetic information like a chemical shift and then spin-spin coupling, nothing but a J coupling and then isotropic chemical shift. Again, no, in spin 1/2 in solids, you will get all this information, magnetic information, nothing but a chemical shift and then spin-spin coupling, isotropic shift, chemical shift anisotropy, J coupling, dipole-dipole coupling. All these interactions you can see from spin-off nuclei in a solid. Spin-off nuclei in a solid. If you take a quadrupolar nuclei, then you will see that electrical electronic shielding information and then quadrupolar coupling together, in addition to all this other information. So here is a comparison of relative magnitude of your dipole-dipole interaction, chemical shift, and then J coupling, and then quadrupolar coupling. You see that they are really, and size is a matter. So again, RF influence also you can see them. RF interference means you are applying a radio frequency pulse from the spectrometer, and that also influencing your sample. So that will give you the static field as well. So static field is again now comparable to the quadrupolar nuclei. You see that the size of the nuclei. So basically, you play with the spin and the spatial information by rotating your sample. By rotating your sample, I can remove the interaction, I can reintroduce the interaction. Where I need, I can use it. The same way, I can irradiate with the radio frequency pulse and remove this particular interaction and reintroduce them. How? Let me show you. This is the one specific concept. Keep remember this. One is on resonance, one is off resonance. What is on resonance? On resonance means assume that one disk is rotating. You are on the disk and you are feeling the rotation. That means on resonance. Assume that the same disk is rotating, but you are not on the disk. You are outside the disk, out of the disk, and you are watching the disk is being rotating. So this is the off resonance. So there are two things. One is observer. Observer is you are the observer, and whatever disk you are saying, that is what the some object that will be when you see on resonance, you can see the object in like a stationary. But when you see outside the off resonance case, like outside the disk, you will see that the disk will be rotating continuously. So the interactions also same. These interactions can give you some result based on this on resonance or off resonance. So basically, when you get a on resonance, where you are omega r by 2, then you will not get any information about the chemical shift anisotropy. So means you can play around with the chemical shift anisotropy, whether I want to use it or no, whether I want to use the quadrupolar interaction or no. That you can decide here by running this experiment and putting your resonance frequency where I want to set it up. So I told you, I can spin the sample and I can irradiate the sample. By spinning, I can remove some certain interaction. By spinning at a different angle, I can reintroduce them. The same way, by applying a radio frequency pulse, I can remove certain interactions. I can also reintroduce them. So this is actually by effect of a radio frequency. This is the effect of radio frequency, and this is called coupling and recoupling. Means I can reintroduce them. Reintroduce means recoupling. So assume that you have a proton and a carbon. They are like a different nuclei. If they are similar nuclei, it is called homonuclei. If they are different nuclei, like one is proton, one is carbon, means they are heteronuclei. Hetero means different nucleus. So Assume that you have a heteronuclear dipolar coupling is there in a powder sample, and you are putting into a magic angle spinning, and you are removing partial chemical shift anisotropy. The dipolar interaction means chemical shift anisotropy. You are removing them, and you are resolving that structure, and you are also doing decoupling. Decoupling means whatever the coupling happened because of the proton to the specific interested nuclei will be removed by radio frequency pulses. That is called decoupling. So now I told you two mechanisms. One is magic angle spinning, another one is decoupling. By implementing these two, you can remove a particular interaction, chemical shift anisotropy interaction. So there are some experiments. You can use that decoupling experiments, proton decoupling experiments under the magic angle spinning. Then you can remove all the interactions from the static spectrum. You see that isotropic spectrum, you can get a good quality spectrum from by doing your magic angle experiment with the proton decoupling. The same thing, if you increase the spinning speed, then you will resolve the structure also by this continuous line to no lines spectrum, that you can get it. CRAMPS is a high definition NMR that can give you very well resolved spectrum. Let me go further. This is a cross polarization. Cross polarization means you can magnetize your non-magnetic nuclei. Non-magnetic nuclei means less sensitive nuclei to a high strength nuclei. So that is the technique is called cross polarization, CP. CP means cross polarization. So that means that you are spinning the sample in a one particular frequency, and then you are applying a radio frequency pulse in a different way by changing the nucleation frequency in such a way that the proton resonances are transferred to carbon resonances. So what happened in 500 megahertz, your proton frequency is 500.13. Your carbon resonance is 125 megahertz. What happened now? You are applying a nucleation frequency by using radio frequency pulses in such a way that the proton resonances are transferring to carbon resonances. That means that you are making both nuclei in a similar framework, and they can meet each other and they can exchange each other without any loss. So that is what this cross polarization means. So this particular mechanism is called Hartmann-Hahn matching. Hartmann-Hahn condition. So that means that you have this is a pulse sequence for a proton channel. You have a 90, and then you have a contact pulse, and then decoupling. So initially you are exciting proton by 90, and then you are exchanging your magnetization from proton to carbon during this contact time. And this time, in a transverse plane, all the proton spins and carbon spins will interact each other. They exchange their magnetization. That means that a proton magnetization will be transferred to carbon. So carbon will become a sensitive nuclei. Originally, it was a 1% natural abundance. So now it will become like 100% natural or 50% natural abundance, like nuclei. So you will get a good quality signal when you apply decoupling pulse together. Decoupling means I already told you the interactions will be removed. Dipolar interactions will be removed. There are some several approach. This is again Hartmann-Hahn condition only. How to optimize and then how to set it up, that experiments. So here is you see some difference is there. So here is a ramp wave they use. Here is a rectangle shape they use. So some difference. This will enhance the sensitivity of your signal. Again, one more sequence has been added, FSLG. FSLG is a frequency switching Lieb Goldenberg sequence. This sequence can enhance proton sensitivity, means carbon sensitivity from the proton. So yeah, I think all these are up. Yeah, this is the decoupling sequences, the phase modulated decoupling sequences. There are several different decoupling sequences are available: TPPMs, spinel, XIX, SW. So all of them are basically, you are putting your radio frequency pulses in a different way, and different mechanisms is implemented in inside the sample, and then basically you're manipulating the spin coupling between one another. So TPPM is the best one, I would say. For I use most of the time TPPM only. These are the other approach. So CP can be done in a triple resonance also. Like initially, you can take the magnetization from proton to exchange to carbon, and then from carbon to nitrogen also you can exchange them. So carbon has a 1.1, nitrogen has a 0.3. So you can transfer the polarization from proton to carbon through proton to nitrogen through carbon by using this double CP method. There are some fast acquisition T2 experiments are there. The name is called Carr-Purcell-Mayboom experiments. The pulse sequences should be like this. Initially you put a 90-degree and then you put a 180, and then it will be. Or you can also put one more 180-degree, and then you can cycle them in a particular time, and then you will get a result. Basic result always either 1D or 2D, or 1D in the case of 1D you will get a FID. In the case of 2D you will have a T1 dimension and T2 dimension. Both dimension you will have a real signal in a 2D form. I will skip them here because all of them are the same. This is multi-quantum magic angle spinning. So this is actually no specific experiment in order to elucidate your quadrupolar interactions. So in magic angle spinning, people will use this technique MQ mass in order to get your quadrupolar interactions. If your nuclei will possess a HQ, and that nu Q can be extracted. So I told quadrupolar interaction is not that easy. Quadrupolar is assume that you have a positive and negative together. So that is called the quadrupolar. 4 different charges together placed. So that is called a quadrupolar. So in a static spectra, you can see that spectra means a distributor. Even if you put a magic angle spinning, your resolution will not happen. It means the spectral editing is not happening. Why it is not happening? I'm putting all my energy into magic angle experiments. I'm not resolving. Why you are not resolving? Because you have a quadrupolar interaction inside. So that has to be dealt in a separate way, in a very different way, because your nuclear separation is different. You see that it has a 3/2. So you will have a -3, -1, minus. So you will have a different axial orientation. Yeah, here is this +3/2, 1/2, -1/2, -3/2. So this is the energy level separation. Between them, you will have a exchange of nuclei happening based on this sequences. This sequence of sequential experiments. This is a 2-pulse experiment, and there are 3-pulse experiments also available. So 2-pulse experiment will give you less sensitivity than the 3-pulse experiments. Basically, what you are doing, you are elucidating your quadrupolar interactions. Either you are elucidating first order quadrupolar or a second order quadrupolar interaction. 2 interactions you will precisely you can extract them from this experiment. I'll move on. I'll show you some 2D spectra so that you will understand them. So this is actually I told so broad spectra will be there. This is what I did in sodium citrate, and you see the well distinguished contours are there. This is from here you can fit the contour, and you can get this CQ, eta Q, and then isotropic chemical shift. MQ mass only can resolve the spectrum. Magic angle spinning will not resolve the spectrum. This is a static one. You see this, this is the one sample I did. So I can see that the spectra is completely resolved yeah, in one dimension. I don't think I can take into this these high dimensional NMR experiments. I'll quickly go into that final thing. So so one is homonuclear correlation. Homonuclear correlation, I told you, spin-spin interactions that can be experimentally elucidated and extracted. This is the sequence. One set of pulse where you can excite the molecule, and one set of time you allow them to talk each other, and then one set of time they converse them together, and then you can put record the experiment. So this is actually a 2D experiment and a homonuclear 2D experiment. COSY, TOXY, NOSY, ROSY, all these are coming under this category only. But you can also define your own experiments. Like I have designed one experiment. So this is actually again BABA type of experiment, single quantum, double quantum experiments. So basically, you are seeing from you are identifying interaction between single quantum to double quantum within the molecule. You can say molecule or materials, anything. In most of the solid state emission, you will be using solid state NMR. In most of the solution, you will be using organic system, not inorganic system. You will not be using. So these are all some of the techniques that implemented in order to count your spins, number of spins within the sample. And this is the one of technique that I told you, CP method. So you can use this technique to get your 2D data. This is actually spin counting experiment. You can see that how many spins we detected, like 26, here 22. In this case, it is 8. So there are different experimental condition, and we can also see that it's 12 actually, here 14, and you can see that 32 also we get one particular time. So with respect to different experimental condition, you will achieve that many number of spins. This means that many number of spins, farthest spins, they are talking each other. 32th person is talking to the first person. That's what 32 MQC means. MQC order 32 means 32nd person in between 31 people are there. Cross them, all of them, and then he can talk to other first person, something like that. This is. So this is another experiment. This is actually this one is spin counting on a one quantum dimension. This is a double quantum dimension. This is either side you can see. So you know that what is a ladder operator or lowering operator. Only one side you can go. One experiment. Another experiments you can go upside or you can go downside also. You see that either side we are recording data. Either side we are getting information like positive and negative dimensions. So these are some of the theory. I don't think I can go into much into this. The final one I want to explain to you is a diffusion ordered spectroscopy. So diffusion ordered spectroscopy is the one very important technique when you really want to work with battery material or solar material. So this technique allows you to detect the diffusion coefficient. There are no other direct measurement of a diffusion coefficient except solution NMR, diffusion NMR. So this dose NMR. So what you do, you initially position dependent encoding is happening by using a pulse sequences, and then you will detect the end of the day. You will detecting the signal. Initially, all the spin starts at one point, and then finally they end up with a different position. That means that they are moving in a different velocity. So you will identify that how much distance they moved and what is the radius of the ions, like either cation or anion. You can exactly measure them by using this technique. So this is the relationship what you get end of the day. Diffusion coefficient D is equal to kBT by 6 pi eta Rs. Rs is the radius of the cation and anion. You can use this formula to average them out. So yeah, specifically cation and anions, you can get a data, and you can see that assume that one is a cation and another is anion. This is a anion. This is a cation, and you see that radius is very large, and in this case radius is very small, and you will get a diffusion coefficient accordingly. By measuring them, you will get a these are all some of the conversion. I can tell you that molar diffusivity. Molar diffusivity means that it accounted with other parameter also. So lambda NMR is the molar conductivity. So you need to use this relation with respect to temperature dependent. You need to measure them, and then you can also use lambda impedance also, and then you can find ionicity. How much ionic nature your sample had. You can distinguish them. So finally, I want to conclude with the bio-NMR. Apart from single crystal diffraction, there are no other technique that you can use for detecting the proteins. So my NMR is the one which can compete with X-ray crystallography, but not to the maximum. NMR still single crystal X-ray is the dominating number of crystal structure solution, but NMR also can do some extent. You can say that during 2021, you can say that 7,000 proteins are solved by using NMR. Again, people are working with that in that particular area. So definitely, NMR can be used for solving the proteins. Actually, no. Nowadays, only for 10 years or 15 years only, we get a 1 gigahertz spectrometer. So if you get a high field, definitely you can resolve any protein structure. So we need to thank Ulrich, who invented the protein structure solution methodology with the high field NMR. So definitely you need to do proton carbon nitrogen correlation, otherwise you will not solve the protein structure. These are all some of the examples of protein structure. This is the 2D structure and this is the 3D structure, and you see that 3D is a well resolved one, and initially it is exciting. For the first dimension it is exciting, second dimension it is a mixing, and again third dimension only you are acquiring. So that means that from one nuclei you are transferring to other nuclei, and then from that nuclei to third nuclei, and then you start recording them. So you can use a nitrogen in between also, proton carbon carbon hydrogen, or proton carbon nitrogen hydrogen. You can also use that one. You see, this is a hydrogen carbon proton, so 3 nuclei. So from proton to carbon you need to exchange, and then through bond you excite nitrogen, and then you excite them excite the other atom, and then you get a data. So you can definitely you need to use a gradient system. Without gradient, definitely this enhancement would have never happened. So finally, I thank Dr. Prakash for this wonderful opportunity, and Dr. K. Ravichandran for this immense talk. If you have any doubts and clarification, please ask me.